Hello, how you doing? Mohammed Porgaz here with another video on concrete mixture design and proportioning, step 5. We discussed previously that concrete mixture proportioning is a total of 10 steps, and we have covered the first 4 steps. If you have not watched the previous videos, please go ahead and do so before continuing and watching this video. Today we will be talking about step 5, selecting water to cement ratio. And there we go. We get started here. So selecting a water to cement ratio is in fact a balancing act. We want to balance the long-term requirement such as strength, durability, and volume stability. For example, we would like the system to have a low shrinkage, volume stability. And on the other hand, we want to balance the short-term requirement of workability, placeability, pumpability, finishability, and all of those abilities. Now, a concrete that has a low water cement ratio will have a higher strength, but it will be less workable. It will be more difficult to pump. And a concrete that will have a high water cement ratio will be easier to place it, and it will be more workable, but it will have less strength and durability. So it is a balancing act, and if we can balance this, like our friend over here, we win. So now, we would like to talk about that. And to do that, we want to get a little bit deeper in water to cement ratio and figure out why all cool cats of concrete industry talk about water cement ratio. First, an example of a cool cat of concrete industry you can see over here. Now, we have to remember that water cement ratio is always measured by mass or by weight, and generally water cement ratio gives us the first assessment of the quality of the material we are dealing with. It is an indirect measure of porosity, and I will talk about this a little bit more. And in fact, what controls the engineering properties is volume, and I will talk a little bit about moving between mass ratios and volume ratios, and then you will see why this becomes very important, why you will see the significance of water to cement ratio. Now, we're going to use a conceptual model that is based on the work of Professor Ken Hover out of Cornell University. He has a very interesting paper that was published in Concrete International. The title was Making Sense Out of Water to Cement Ratio, and I will follow that a little bit in the next few slides over here. Of course, in this conceptual model, we are doing a lot of approximation and generalization. For example, we will consider that our cool cat over here is circle, is spherical. And of course, in this model, we will consider that the cements that have irregular shape, they have regular shape, and they are uniform, and they're circular. And of course, the second assumption that we are doing over here is that the structure is uniform throughout, which is not completely accurate. But this conceptual model will provide you with some good visual understanding of what happens when we change the water to cement ratio. We will look at the relative volumes, and there are more complex models that I will very slightly touch on one of them, which is not completely accurate, and again just provides a good understanding why water to cement ratio is such an important factor. So now, if we want to use the concept of making sense out of water to cement ratio, we will consider a US dollar bill. A US dollar bill is approximately 157 millimeter wide and 66 millimeter tall, and we will use the US penny, which is 19 millimeter in diameter, and we will start to put those pennies on the dollar bill, as you can see over here. Now, this physical model, or conceptualization, we want to relate this to a concrete that comes from a ready-mix supplier. For that, we will consider the background, the dollar bill, as water, and we will call these pennies as cement, as shown over here. And now we will go ahead and place these pennies on the dollar bill, and we would like to see how does this look like. we start over here with 9 pennies, 11 pennies, and we will continue to the maximum that we can place over here in this particular case, which is 27 pennies on the dollar. Now, if the background is water and these pennies are cement particle, we can calculate the water to cement ratio. And you can see that over here we are talking about water cement ratio of 1, and over here we are talking about water cement ratio of 0.13. And what we observe over here is that as the water cement ratio decreases, the microstructure of our conceptual cement paste is becoming denser and denser. This is the effect of water cement ratio. That is why lower water cement ratio mixtures have a higher strength, because they have lower porosity. And whomever controls the porosity wins the game. The lower porosity you have inside the system, lower permeability you have, less water moves through the system, and higher durability therefore. And of course, the lower porosity that we have inside the system, the strength of the system increases quite a bit. So now, if you look at the concrete, the normal concrete that is generally being used in day-to-day practice, they range something between water cement ratio of 0.4, 0.35, maybe up to 0.55. And this is how the microstructure of those will look like. And you can see that in this particular case, at the higher water cement ratio, we have a lot of empty spaces between these pennies, whereas those empty spaces decreases quite a bit. And the lower porosity you have, generally the higher strength and better durability you have in these systems. All right. Now, let's look at this in the form of a percentage by weight and percentage by volume. On the left, on x-axis, you see the water cement ratio. On y-axis, you see the percentage by weight. When we talk about the water cement ratio of 0.7, you can see that by weight, something around 60% of the system is made of cement, and something around 40% of that is made of water. When we talk about the water cement ratio, for example, 0.35 over here, we see that something around 70% or 75% of the system is made of cement, and the rest is made of water. However, when we convert this to volume, we see something drastically different. In the case of water cement ratio of 0.7, we see that something around 30% is made of cement, and something around 70% of the system is volume. This is because of the huge difference, 3 times difference between the specific gravity of water and cement, of course. And in the case of, for example, water cement ratio of 0.35, you can see that approximately 50% of the volume is made of cement, and 50% of the volume is made of water. This is how we make concrete. This is where engineering properties are. This volume, the ratio of the volume, is really governing the engineering properties. And you can see that as the water cement ratio increases, enormous amounts of the system, enormous volume fraction of the system is made of water. And therefore, the mechanical properties and durability of the system degrades very rapidly with increasing water to cement ratio. Now, the previous slide was really conceptual, and we did not consider the chemical reaction that takes place between the cement and water. What if we account for this chemical reaction that happens between these two? And what I would like to mention over here is the fact that this conceptual model this model, which is a little bit more accurate than the conceptual model and takes into account chemical reaction, is still not 100% correct, but provides some understanding of what happens inside the system. We will start this by considering an example of water to cement ratio. And we will go ahead and arbitrarily choose water cement ratio of 0.63, and in a second you will see that that water cement ratio is not really an arbitrary water cement ratio, and it is cleverly chosen. So we have a water cement ratio of 0.63, and we will go ahead and choose 1 cubic foot of cement by volume. Remember that this is volume. And water cement ratio is a mass ratio. This is very important. So we have a water cement ratio of 0.63, and we will go ahead and buy 1 cubic foot of concrete. And of course, we know the specific gravity of the cement, and we can calculate how much a 1 cubic foot of cement weighs. And it turns out to be 196. And we will use water cement ratio now to calculate how much water do we need to have water cement ratio of 0.63. And when we use this water cement ratio and the mass of the cement, we end up with 124 pounds of water. And now I'm going to go ahead and convert this back to the volume, and suddenly you see that now we have 2 cubic foot of water for 120 pounds of water. So now we ended up with 1 volume of cement, 1 cubic foot of cement, and 2 volume of water, 2 cubic foot of water. And now we will go ahead and put them together, and let's assume that we have a magical power, that we say that you guys sit on top of each other and don't move, don't have any reaction. And then over here, the water and cement are separated at this initial state. And then we fire the clock and we tell them to react. And the reaction starts, and we will go ahead and assume, and it turns out to be approximately correct, that 1 volume of water reacts with 1 volume of cement, based on volume. Therefore, 1 volume of cement and reacts with 1 volume of the water. And we have 2 volumes of 2 cubic foot of reaction products. We end up with a 1 cubic foot of extra water. Now, this extra water does not sit on top of the concrete and does not separate itself from the concrete. It becomes big porosity called capillary porosity, remains inside the system and makes the system weak. That is why when you decrease the water cement ratio, effectively what we are doing, we are eliminating this extra water that remains after the complete reaction. So this extra water left over becomes part of the structure, and at higher water cement ratio, we will have a lot more extra water sitting in the system and causing porosity and basically degrading the durability and the strength of the system. And in lower water cement ratio, we do not have that issue. Now, that we got a little bit of understanding why water to cementitious is important. And just to clarify over here, water to cementitious is, for example, if we have something like fly ash or silica fume inside our system, we basically use those as a cementitious material, and instead of cement, we divide the water by total mass of the cementitious material, and that is referred to as water to cementitious material, just to clarify that there is something in addition to cement inside the system. Now, the selection of water to cement ratio is governed by both strength and durability. For both of them, we want a conservative, in the case of strength, we want a conservative estimate of the strength, and generally these are the existing tables that are out there are for type 1 at 28 days strength. We also want to make sure that the water to cement ratio is selected properly so that we end up with a concrete that can tolerate severe exposure. For example, if you're casting a breach deck out of this concrete, or it is exposed to seawater and so forth, you want to make sure that it can avoid corrosion or rebar. So we want to make sure water cement ratio that we select meets both strength and durability, and we want the most conservative. If the durability says that we need a lower water cement ratio, we have to select that water cement ratio. If the strength says that we need a lower water cement ratio, we have to use the lower water cement ratio. Basically, we want to have the most conservative estimate of the water to cement ratio. On the x-axis, you see the water to cementitious material ratio. You can for now consider this as a water to cement ratio. On y-axis, on the left, you see 28-day compressive strength in megapascal. On the y-axis, on the right, you see the 28-day compressive strength in basically in KSI or 1000 PSI. And we can see that for both air-entrained and non-air entrained concrete, as the water-cement ratio increases, the mechanical properties degrade very quickly. And we already know that the concrete that has air, generally the strength of the concrete is a little bit lower because air voids, again, are processing inside the system. But you can generally see that for both concrete, with the increase of water-cement ratio, the mechanical properties decreases quite a bit. Here is a table that is from ACI, and it provides basically for both air-entrained and non-air-entrained concrete the water-cement ratio that you need to choose to achieve a certain strength. For example, if you want 5 KSI or 5000 PSI concrete, if our concrete is air-entrained, we have to use a water-cement ratio of 0.4. If the concrete is non-air-entrained, we have to use a water-cement ratio of 0.48. And we can use this to give us some estimate of the water-cement ratio that we need to select. Now, the previous slide was in empirical units. This slide provides exact same information, but it's provided in metric units. You can see that the strength is in megapascal. Water-cement ratio is the same in both of them. Of course, it is a ratio and does not have a unit. Okay. In addition to that, we said that the water-cement ratio has to satisfy our durability requirements. Now, if our concrete is exposed to sulfates, there is a maximum water-cement ratio that we need to meet. Water-cement ratio cannot increase beyond this point. For example, if the sulfate exposure we have to figure out whether the sulfate exposure is negligible, moderate, severe, or very severe, depending on if the concrete is exposed to the soil or is exposed to the water that contains sulfates. Okay? Now, in those particular cases, there are maximum water-cement ratio and minimum strength is specified. For example, if we have a moderate sulfate exposure, and we can measure that by percentage mass of soil, for example, 0.1 or 0.2. And in those cases, we have to use a maximum water-cement ratio of 0.5. The same thing for severe and very severe is provided, and you can always refer to these tables if you are dealing with sulfate exposure, either in the soil, concrete that is in the soil. For example, if you have a foundation that is placed in soil that has sulfate, or concrete that is in contact with water that has sulfates, that is measured as ppm, and we have to meet this maximum water-to-cement ratio and minimum strength. Now, with regard to freeze and thaw durability, we have the same sort of requirement. Depending on the type of the exposure that depending on the type of the exposure, the concrete has to have a maximum water-cement ratio. For example, if we are dealing with a very severe case of the concrete exposed to frequent freeze and thaw cycles and exposed to very severe sulfates, or we are worried about the corrosion of reinforcing steel, then the maximum water-cement ratio is 0.4. You cannot use a mixture that has a higher water-to-cement ratio, even if you can meet this strength requirement. So you have to always check, after figuring out what the strength is, we have to figure out whether we are meeting the durability requirement for freeze and thaw and sulfates, if those are the case. In the case of the concrete that is, for example, exposed to limited freeze and thaw exposure, that's F1 exposure, the maximum water-cement ratio is 0.55, and this is a strength requirement that we need to meet. So after basically figuring out the strength and corresponding water-cement ratio, we have to just check, and if that is bigger than that, we have to reduce the water-cement ratio to this maximum. Okay. This is a graph that was originally made by Professor Ken Hover. And on x-axis, you see the water-cement ratio. On y-axis on the left, you see the average compressive strength. On y-axis on the right, you see the coefficient of permeability. You can consider this as basically permeability under pressure gradient. And very nicely over here, our minimum specified strength are shown over here. If we have a condition of moist, freeze, and thaw, we have to have the maximum water cement ratio of 0.45. If we are worried about the corrosion of rebar in cases, for example, in the bridge deck that's exposed to de-icing salt or the seawater, that we are worrying about the corrosion, and we need to have corrosion protection, the maximum water cement ratio is shown over here as 0.4. So this is just a schematic illustration of the information. The additional thing that I will show over here is that with increasing the water cement ratio, we see that the coefficient of permeability increases very rapidly. And again, this is because all the leftover water, all the big pores that are inside the system, and the permeability of the system is increasing very rapidly with increasing the water cement ratio. Now, if someone tells us that they need a concrete with compressive strength of, for example, 3,500 psi, should we give them a concrete? Should we design our concrete for that 3,500 psi, or should we be a little bit more conservative? Now, we know that concrete material are basically heterogeneous material, and there is some variation in the strength when we do strength measurement. So if we do strength measurement on a particular concrete that is made with a certain mixture, if we go ahead and do a lot of compressive strength measurement, we will end up with some sort of normal distribution, or for those of you who want to be a little bit fancier, we're going to call it Gaussian distribution of the strength. Now, we know that the average or the mean value for that is what we use for the average strength of our concrete. However, if, for example, 3,500 psi is specified, we should not go ahead and design the concrete for 3,500 psi, because in those cases, 50% of the time, the strength of the concrete will be below that average value, and we will be safe only half of the time. So we have to move basically our required strength, or we have to consider our specified strength further down in the bell curve, or this normal distribution, to make sure that we are always safe. And basically, if you are a material supplier, you want to get paid all the time, and it is better, and if the strength is low half of the time you're not going to get paid. Therefore, we want to make sure that we always have a strength that is a required strength that is much higher, or higher, I shouldn't say much higher, higher than the specified strength. And that is bringing us to the concept. Before selecting the water cement ratio, we have to do this adjustment. That brings us to the concept of required strength versus specified strength. Specified compressive strength is a compressive strength that is specified by the engineer or the owner. They will tell you that I need a 3,500 psi concrete. Now, what we want to do, we want to bump that up a little bit to be safe, and then we call that a required compressive strength. And we use that using the so-called standard deviation. In a second, you will see how we do that. So we want the specified compressive strength to be down here, and we want to design for the required, or proportion for this required compressive strength, which is much higher than specified concrete strength. Now, there are also other limitations. If someone comes and tells you that they need a concrete with 2,000 psi, you don't want to design that for 2,000 psi. The specified concrete strength should not be less than 2,500 psi. F'(C), the specified, is basically has to be based on 28-day strength measurements of cylindrical specimen, and generally, the required strength has to be something around 500 to 700 psi, bigger than the specified strength. Now, how do we do that? How do we figure out what is the required compressive strength when the specified compressive strength is given to us? We will do the following. First, we will look at whether there exists data on concrete with a similar concrete. When we define that similar concrete with a concrete that has a compressive strength of within 1,000 psi of the concrete that we want to proportion. For example, if someone specifies a compressive strength of 3,000, we want to see whether the ready-mix producer that wants to produce this with a local material that we have has any concrete material that is, for example, 3,500 or in that vicinity, within 1,000 psi. In those cases, we will choose a different approach. If there is no field strength measurements are available, and there is no data for similar concrete is available, we will use this table, which means that if the compressive strength less than 3,000 psi is specified, add 1,000 to it. If it is between 3 ksi and 5 ksi, add 1,200 to it. And if it is greater than 5,000 psi, use this equation to figure out what is the required compressive strength is. So in this particular, it is very easy. Now, however, if there are field strength test results are available, we will use a little bit different approach. First of all, we will ask how many test data are available. If it is less than 15 test data available, we will ignore all the field strength test results that are available, and we will go back to this table, and we will consider, we will assume that there is no field strength data available. If 15, 20, or 25, or 30 or more is available, this table will give us a coefficient. Let's think about this as a correction factor. Then we will ask, okay, what is the standard deviation of your measurements? I think all of you can calculate standard deviation if you have a bunch of data are given to you. So we will ask, what is the standard deviation? And after we get that standard deviation, we multiply that by this correction factor. For example, if the concrete producer tells us that standard deviation is equal to 500 psi, we will use a factor S that is corrected with one of these factors. Let's assume that they will tell us that they have 20 test data available and their standard deviation is 500 psi. I will get that 500 psi and multiply that by a correction factor and use this S in the next slide. Okay? So this S, in this case, is a corrected standard deviation. Now, over here, now in the case that we have a field strength data available, we want to calculate the required compressive strength from specified compressive strength of the concrete. So the required compressive strength is equal to the specified plus 1.34 S. Remember that S is equal to the correction factor times the standard deviation. Okay? And we will use that over here, and we use that in both equations, and of course we will use the larger value between them. That's pretty straightforward. Remember that that has to be for concrete with similar, which means that within 1,000 psi of the concrete that we are designing. Let's go back to our example over here. We said that the specified compressive strength for us was 3,500. We will assume that no data, no field strength data is available. In this particular case, it becomes very easy, of course. 3,500 is somewhere between 3,000 and 5,000, and we will use this equation, which is plus 1,200. And therefore, this is our F prime C required. This is our required strength that we need to design this concrete for, or proportion this mixture for. All right. So now, what is the water-cement ratio? We said that our required compressive strength is 4,700. That is somewhere between 4,000 and 5,000. And the waters and the concrete that we use is air-entrained concrete. Remember that we said that we will consider 5.5% air in our concrete. So it is an air-entrained concrete, and we have to use this column on the right. And we have to interpolate between 0.4 and 0.48 and figure out what that water cement ratio for 0.47 is. It is rather easy to interpolate between these two numbers using elementary, basically algebra, that you can figure this out very straightforward. There are other ways that you might want to consider to do a quick calculation if you don't want to write down your interpolation equation over here. One way is to divide the difference between these, divide the difference between these two and these two together, and estimate this very quickly. I'm going to just show this in this particular case. 0.48 minus 0.4 divided by 1,000, that will give you 0.08, and that number is basically the change in water cement ratio for every 100 psi. So you can see that this 4,700 is 300 psi change from 5,000, and if I multiply this times 3, I will get 0.24, and if I add that to 0.4, I will end up with 0.424. Now, I probably have skipped this a little bit, but you can do you can figure this out very easily. You can because the difference between the left column between the strength of 1,000 psi, it is very easy to calculate what is that number and do that adjustment. All right. So we figured out what is the water cement ratio. Again, the take home over here is that this is the required compressive strength, not specified compressive strength. Now, we said that we have to check against the requirements for durability, and this is a table that we have in our particular case. We said that our concrete beam is exposed to a moderate exposure, that is a class F1 exposure, and the maximum water cement ratio is 0.55, and the water cement ratio that we figured out based on the required compressive strength was 0.42, 0.424, which is smaller than 0.55, and this is okay, we meet this requirement. Finally, over here, the same graph that we saw, we said that in our particular case, we have a moisture freeze, and you don't have to check this. I just wanted to show that you can use this table as well. You don't have to do this as a part of solving an example. I just wanted to show this, that our water cement ratio of 0.424 is below water cement ratio of 0.45 that is required for freeze-and concrete that's exposed to moist freezing. I will stop over here, and I will be back very soon with a continuation of this lecture.